Okay, so finish out our test here today. First one is so-called ratio test, and really it's because we're going to be looking at the ratio of, well, it's basically the ratio of subsequent terms in a series. Here's the statement. It's got three parts. We're looking at the first part, if the limit n goes to infinity of the n plus 1 term divided by the nth term. So basically we're taking a term, divide that into the term that's after it, n plus 1. Just means plug in n plus 1. That's really what I mean. If that limit, that's the limit we're going to be looking at, is less than 1, then convergence is absolutely convergent because, yeah, we got absolute values there. All right, number 2, if the limit as n goes to infinity of this ratio is greater than 1, the series diverges. Okay, number 3. If the limit, so there's one other scenario, and that is if the limit equals 1. Well, if it equals 1, we have a problem. This test is inconclusive. Gives no information. So that's the ratio test. The ratio there that we do, the limit of that ratio, is less than 1, greater than 1, or equal to 1. Less than 1, good, got it convergent, absolutely. Greater than 1, divergent, equals 1, punt, do something else. Okay? All right. Now, one of the series that this is really comes in handy with is the factorial series. We haven't done many of those because we haven't talked about the ratio test yet. So, but a factorial is, just to review that real quick, 5 factorial, 5 exclamation point, means 5, 4, 3, 2, 1. It's the countdown product, I like to call it, starting at 5 and multiplying all the way down to 1. Now, with our case, of course, we'll be running into n factorial. And n factorial, of course, will be n, then times n minus 1, then n minus 2, whatever n is. Just keep subtracting 1 from each one until you get to 1. But really, what we'll really kind of need to understand here is what about n plus 1 factorial? Well, n plus 1 factorial would be, that would start at n plus 1, and then what would be the next one? N would be the next one, and then n minus 1, and then n minus 2, so on and so forth until you get to 1. But the real key to this is notice what this is right here. N minus 1, what is n minus 1? All the way to 1. Isn't that n factorial? That is n factorial. So the way we'll use this a lot is we're going to say n plus 1 factorial is n plus 1 times then the n factorial, right? Because that's really what n plus 1 does, is it adds one term to the n factorial. All right. So with all that in mind, I'm going to have to erase my test here. But with all that in mind, let me do a ratio test example or two here along the way. Okay, so we've got series n factorial over 3 to the n. So we're going to use the ratio test here. Like I said, for factorials, it's usually the way you want to go, ratio test. Okay, so what do we want to do for the ratio test? Well, the ratio test, we want to look at the limit as n goes to infinity of the absolute value of a n plus 1 divided by a sub n. We want to know what that limit turns out to be. Well, then, in this case, a sub n, this is a sub n, right? So that's my bottom part. A sub n plus 1, well, that would be plugging in for n. Instead of n, we have n plus 1. So a sub n plus 1 is going to be n plus 1 factorial over 3 to the n plus 1. I am looking at the absolute value of that. Okay. Well, we've seen this right here to simplify. First of all, couldn't I say this is the limit as n goes to infinity? Absolute value of n plus 1 factorial over 3 to the n plus 1. And then times, this is divide by this, so what would it be times? Wouldn't it be times the reciprocal of that? 3 to the n over n factorial. Okay? Now here's where the canceling comes in. Remember what we just said, n plus 1 factorial, we can actually write it in terms of n factorial, can't we? Isn't n plus 1 factorial n plus 1 times n factorial? 3 to the n plus 1, couldn't we write that, split that up to 3 to the n times 3 to the first? Because that's going to also help us in our cancellation here. What can I cancel out then? Well, I can cancel out the n factorials, and I can cancel out the 3 to the n's. So I'll wind up with the limit as n goes to infinity of the absolute value n plus 1 over 3. All right? That's all I wind up with. Well, what about the limit as n goes to infinity of n plus 1 over 3? That is, of course, infinity, isn't it? Infinity plus 1 divided by 3. Well, infinity plus 1, that's infinity. Divided by 3, that's still infinity. Yeah. All right, so what about that? Well, ratio test says if my limit is more than 1, greater than 1, which infinity certainly is greater than 1, it's divergent, okay? So this series, n factorial over 3 to the n, diverges by means of our looking at the ratio test. All right? Not too bad. Let's try another one. How about series negative 1 to the n factorial over 2n plus 1 factorial. Does that series converge or diverge? Again, there's our factorial. Matter of fact, we've got 2 factorials. What's going to happen here? Well, first of all, if we look at the limit as n goes to infinity of the absolute value of a n plus 1 over a sub n, that's going to be the limit as n goes to infinity of, well, plug in n plus 1 here, here, and here. We get negative 1 to the n plus 1 factorial over 2. Now it's 2 times n plus 1 factorial. Okay, and we'll talk about what that means here in a second. That's all the top. So big mess on the top. All right, well, a to the n is just that, so it's negative 1 to the n factorial over 2n plus 1 factorial. Okay, so a couple of side notes here. The absolute value, I mean, we've got alternating, kind of dueling alternating signs, but that's where the beauty of the absolute value comes in. These, the alternating sign thing, that's just going to be wiped out, isn't it? Because we're doing the absolute value of it. So limit as n goes to infinity then is of, we have n plus 1 factorial over, that would be, now if we distribute, you'd have 2n plus 2, but then you got another plus 1, so that's 2n plus 3 factorial, isn't it? And then this divides n factorial, that's just times the reciprocal, 2n plus 1 factorial over n factorial. The absolute value, which I guess you could make the case here that we don't need the absolute value now because those are all positive terms, but nonetheless we'll keep those going, I guess. All right. Okay, so let's, we are going to do our little thing with n plus 1 factorial. That's n plus 1 times n factorial, isn't it? Well, let's do a little sidebar here on 2n plus 3 factorial. Come over here for just a second. All right, so 2n plus 3 factorial, wouldn't that be, count down, 2n plus 3, 2n plus 2, 2n plus 1, and then 2n, blah, 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 okay? Well, here's the thing. The reason we did n plus 1 factorial to this is so we could cancel the n factorial. Well, on the top here, I've got 2n plus 1 factorial, so isn't 2n plus 1 factorial from here on out? Isn't that 2n plus 1 factorial? So 2n plus 3 factorial is 2n plus 3 times 2n plus 2 times 2n factorial. 2n plus 1 factorial. That is another way we could write 2n plus 3 factorial. All right, so then we've got 2n plus 1 factorial over n factorial. Nice things cancel here. Factorials gone. So we wind up with the limit as n goes to infinity of n plus 1 over 2n plus 3 times 2n plus 2 and I guess to get the full effect here of this, what's happening, go ahead and multiply your denominator out there, full that out, that would be what, 4n squared, 4n and 6n, that'd be 10n plus 6, I believe. And so if we divide through by n squared, top and the bottom, it's usually the way we look at that. We got 1 over n, sorry, 1 over n, it's 1 over n squared, 4, 10 over n, 6 over n squared, 0, 0, 4, 0, 0, 0, 0 over 4. Limit's 0. Limit turns out to be a 0. What does that tell me about my series? Well, the ratio test says if the limit of all this is less than 1, if it's less than 1, it is absolutely convergent. So this series is absolutely convergent. Okay. All right. Okay. So that's the ratio test. So our last test we'll talk about now is the ratio test. I mean the root test. We just talked about the ratio test. The root test. Okay. Okay. All right. Well, the root test is a good one for such a series as this. Say I've got the series two n plus 3 over 3n plus 2, but then all that is raised to the nth power. So in other words, we've got something pretty complicated anyway, and then we're raising it to the nth power. So we're making things complicated, but the root test is, as you'll see, a good one for such a series as that. Here is the root test. It's got three parts also. If the limit as n goes to infinity of the nth root of the absolute value of the in a sub n, if that's less than 1, just like the ratio test, then the series a sub n is absolutely convergent. And number 2, if this limit as n goes to infinity of the nth root of the a sub n's absolute value greater than 1, well, just like the, did it again, didn't I? Then the series is divergent. And thirdly, guess what? If the limit equals 1, then root test is inconclusive. So the good thing about it is very similar to ratio test as far as the conclusions there. What's different is, of course, this right here, but it's the nth root of the absolute value of a sub n. So, all right, okay. So let's do one. I'm going to change it up here. Okay, so use the root test for series of 3 over 4n to the n power. Well, nicely, what I'm looking at again is this limit as n goes to infinity again, but it's the nth root of the absolute value of the a sub n term, which in this case, this is a sub n right here. So it's the limit as n goes to infinity of the absolute value of that, 3 over 4n to the nth. Well, those are all positive terms, so it's really just the limit as n goes to infinity of the nth root of 3 over 4n to the nth. These terms are positive, so the absolute value really doesn't accomplish anything there. The absolute value of all those terms would just be 3 over 4n to the nth. Well, this is why this root test is so handy, because what happens if I'm doing the nth root of something to the nth power? Well, basically the nth root and the n do cancel out, so I'm just looking at the limit as n goes to infinity of 3 over 4n. Which, what happens as we go to infinity? Well, if n's going to infinity here, doesn't that go to 0? Which is less than 1? Which means, so, this series, 3 over 4n to the nth, is absolutely convergent by root test. All right. Here is another. You good? Okay. I'll just put it down here anyway. See if I can. All right, so let's use the root test for, again. This one's going to be the sum of the 2n over n minus 1 to the nth power. So again, there's our nth power, and the root test basically just takes care of all that. Okay, so we have the limit as n goes to infinity of the nth root of the absolute value of that, which, if you'll notice here, I don't think I put it, but for this to work, for this little series to work, doesn't n have to be something bigger than 1, because it can't be 1. So we even have to start here at 2. And the reason I mention that is because that's going to make all these terms positive. So again, the absolute value bars are not necessary. And so that's going to be just the nth root of 2n over n minus 1 to the nth power, which then the nth root and the nth power cancel out. So we're just looking at the limit as n goes to infinity of 2n over n minus 1. So if we divide, do our little divide thing, divide by n here, we'll get the limit n goes to infinity 2 over 1 minus 1 over n, which is 2 over 1, which is 2, which is greater than 1, which the ratio root test actually then would tell me this series diverges, right? If this limit is greater than 1, then the root, by the root test, this series 2n over n minus 1 to the nth is divergent. Not too bad, huh? All right, well, one more. And that would be the series of negative 3 to the n plus 1 over n to the nth. A little different format. But the root test is still going to help us out here, mainly because using the root test, because I've got an nth to the nth power. If that wasn't part of this, we'd go with some other test. But since I do have an n in the base and in the exponent, probably a good clue to use a root test. All right, so the root test says look at the limit as n goes to infinity of this guy right here. Actually, the nth root of the absolute value of that guy right there. which of course the absolute value would knock this negative 3 power, negative 3 base out. So it'll just be 3 to the n plus 1 over n to the n. The rest of everything is positive. Which, nth root, here's what happens on that. I don't have just the straightforward canceling out thing, do I, here? Because I've got the nth root, of course it does there, but not here. So here's what I'm going to do with that. Let's keep it nth root for now. 3 to the n times 3 to the first. Let's split that up. Doesn't that mean 3 to the n times 3 to the first? I believe so. Which, if we look at it individually there, let's go this way, can be all split up. It's the limit n goes to infinity then of the nth root of 3 to the n, the nth root of 3 to the first, and then the nth root of n to the n. N's galore. Break it all up like that because, yeah, the nth root and the n cancel there, so that's just 3. Now, here's a little something here. How am I going to do that? Well, couldn't I say the nth root of 3 to the first, like the square root of x is x to the 1/2. So the nth root of x is x to the 1 over n. So I'll say it's 3 to the 1 over n. And then, of course, the nth root and the n cancels there, so nth power. All right, well, let's choose to say that is n goes to infinity. Let's break that out as 3 over n, and then times 3 to 1 over n power, and think about that. So as n goes to infinity, what does 3 over n go to? Doesn't that go to 0? 3 to the 1 over n, well, that goes to 0 also, doesn't it? So I don't have a indeterminate form. I've got basically 0 times 3 to the 0, which is 1, times 0, it's a 0, yeah. So that one was a little bit different. Less than 1, conclusive, then test tells me series converges, absolutely.